Hello and welcome to our virtual design day presentation. We are team 19052, a precision brachytherapy device for esophageal cancer. Dr. Jennifer Barton of the Department of Biomedical Engineering is our sponsor. Here's our team. On the top left, we have Ryan, Haram, then Jacob. Starting on the bottom left, we have myself, Audrey, Danny, and then Diana. The bookends of this photo are biomedical engineers, and the two in the middle are mechanical engineers. Throughout this video, we'll be going through this poster. Diana will start with an introduction.
Thank you, Audrey. Esophageal cancer is responsible for more than 16,000 deaths per year and only holds a 19% 5-year survival rate. It can develop anywhere along this region, and each type has a different characteristic. Some may be flat and spread out, others may be large and localized, but most are completely irregular in their shape and location. There are several treatment options available depending on the shape, location, and stage of the cancer. Surgery, chemotherapy, and external beam radiation are all viable options. However, external beam radiation is not specific. A more targeted radiation approach is called brachytherapy. This procedure places a small radioactive seed in very close proximity to a tumor. Here we have a CT scan of a patient undergoing brachytherapy. When we introduce the radioactive seed into the patient, it treats the cancer from within, limiting the radiation exposure to healthy tissue and improving that patient's quality of life. While this treatment is more specific than external beam radiation, current brachytherapy devices still create negative side effects. Here's an example of a current brachytherapy device, and this is the machine that is responsible for controlling the seed. Radiation seeds act like a light bulb, emitting radially out from a source in every direction. Since the seed travels down the center of this device, this applicator would be ideal for a symmetrical cancer type, but not for an irregular tumor presentation. It is because of this irregularity that there is a true need for a more precise device that is able to discriminate between cancerous and healthy tissue. So this is where our design outperforms the current brachytherapy devices on the market today by providing twice the radiation dose to cancerous tissue than to the healthy tissue around it. Now, let's let Danny walk us through the conditions that drove our design.
Thanks, Diana. The project objectives for our device can be described with these 5 words. Our device shall be precise, comprehensive, secure, compatible, and affordable. These keywords led to our functional and system requirements. Our first functional requirement is that our device must provide 2 times higher doses of radiation to the cancerous tissue than to the healthy tissue. Next, our device must function in at least 95% of esophageal cancer patients. The third functional requirement is that our applicator must interface with the provided existing brachytherapy console. It must also insert and retract without causing bleeding to the esophageal tissue and be stable while inserted in the patient. Lastly, our applicator must be cost-effective, disposable device. After deciding on our functional requirements, we came up with our point designs, which Jacob will be discussing next.
Thanks, Danny. So here we're going to go over our initial design concepts and point design. First off, we have our multiple seed channel design, which features 3 inner seed channels that allow us to more precisely place the seed in the esophagus. Second, we have our balloon seed channel design, which is similar, however, it also has an expandable balloon in the center of it. Finally, we have our retractable shielding design, which has only one center seed channel that features an adjustable seed channel window based off of the patient's tumor. Here we have our point design, and we decided to go with the multiple seed channels design after many analyses. This features multiple seed channels, as the name suggests, allowing us to place the radiation seed closer to the cancerous tissue and further from the healthy tissue. It also features low-cost materials as well as material attenuation, and this allows us to further minimize the healthy tissue exposure to the radiation. So now I'm going to pass it off over to Audrey, that way she can go over our device in more detail.
Thanks, Jacob. This is our finalized design. The material cost of this device comes out to less than $120, making the device affordable. The way the device works is that it's inserted into the patient and the balloons are inflated. This secures the device. The inflated region is also known as the treatment area. Our device has a treatment area of 15.7 centimeters. This is a 50% increase compared to other devices. This allows for comprehensive treatment, as patients with larger tumors can now undergo this type of therapy. Within the outer housing of this device, we have 3 seed channels. The seed channels follow the medical standards for radiation oncology and make our device compatible with existing equipment. The 3 seed channels from the previous page can be better visualized in this cross-section. The number of channels is one of the ways we make our device more precise. Other devices have a single centralized seed channel. By increasing this to 3, we are moving the radiation source closer to the cancerous tissue and further from the healthy tissue, thus lowering the dose the healthy tissue sees. The second method we use is silver plating. Silver is a high-density material that does a great job at blocking radiation. All 3 seed channels are coated with 240 degrees of silver. This reduces backscatter from the radiation seed, thus lowering the dose the healthy tissue sees. Our solution is precise, comprehensive, secure, compatible, and affordable. Ryan is now going to explain the radiation analysis we performed to prove that our device is more precise.
Thanks, Audrey. By just looking at the design, it's very difficult to imagine just how the radioactive seeds interact with tissues. To this end, we developed a MATLAB code to calculate the relative dose of radiation from the device to points around the esophagus. This takes advantage of the inverse square law and Beer's law, which describe how radiation dose is affected by distance and the amount of material in the way, respectively. This code iteratively calculates the dose at each point of the esophagus, given the distance between the radiation and the esophagus, as well as the amount of material in the way. These calculations are based on a seed in the channel closest to our quote-unquote tumor, which you can see above. Finally, using this MATLAB code, we compare the radiation given to the tumor and to the healthy tissue to find our 2x ratio. To do this, we first assume our tumor takes up most of the esophagus, so it gets almost all the radiation. Then, we slowly decrease this size and recalculate the ratio to find our limit. Outputs of our MATLAB analysis show the dose profiles due to the inverse square law alone, Beer's law alone, and finally, the two combined, which gives the finalized dose profile. This final dose profile, when compared to the profile of the predicate device on the right, shows how our design works to give a much more precise dose of radiation to our model tumor, sparing 220 degrees of the esophagus from excess radiation. I will now hand it over to Haram to tell you more about the test we performed to validate our device.
Thanks, Ryan. Now I will explain the device flexibility test. This test was done to ensure that the esophageal tissue is not damaged during insertion or retraction. The image on the left shows the test setup using the predicate device, while the image on the right shows the exact same test done with our device. Our device deflected 2.43 centimeters on average. The table below shows that our device is within the 10% tolerance of the predicate device and therefore passes the flexibility requirement. Next, we perform the safe operation test because it's critical for the device to stay secure within the patient so that the radiation treatment is precise. The image shows our device inserted vertically into a model esophagus. The test involved inflating our device's balloons until they clenched the inside of the model esophagus. Then a weight was attached to the bottom of the device and we tested movement for 5 minutes. The device did not displace during this test, which is a pass. Now I will summarize our conclusions. Throughout this project, we have learned to be adaptable and to prepare ahead of time for situations because of unforeseen circumstances. To conclude, we have created a proven device that is more precise than anything else on the market. Thank you for watching our video. We would like to acknowledge our sponsor, Dr. Barton, our course mentor, Mr. Cadwell, and Dr. Thalani, our physician consultant. We couldn't have done this project without your guidance. Thank you.